Well, hi and welcome to my shop here. Today is the 22nd of March, and my last video ended a little awkwardly when my computer hard drive got full. And I didn't get back into the shop until today. So what I'm going to do here is when I was taking the voltage tests, I started finding a few results that were could be a little wonky. So I wasn't making notes at that time. So I'm going to repeat this whole thing. I'll do it all off camera, so you don't have to watch me do it all again. I didn't quite finish first time around, so I'll finish off. Things get a little complicated with this radio in doing these tests. Here's my chart of expected amounts, and I haven't got the results written on here yet, but I'm ready to do that. See that bracketed part there? So it turns out that when you switch bands, some of the voltages on some of the tubes also change. And so I want to make sure I measure those correctly. Some of these changes are pretty subtle. Like it's band 1 that's different than the rest. So you got band 2, 3, 4, I think, and then band 1, the AM band, is different than all the rest. So some of these differences in voltages, like a 0.4 to 1, minus 1, it's not a big change is what I want to say. It's not a big change. It must have been important if the designers wanted that change to occur. That's what I'm thinking. Now, maybe it's not. Maybe they put this radio together, it worked okay, and when they measured all the voltages, this is what they found. So, you don't really know how things got to be the way they are. So I'm going to finish off those voltage tests, then we'll take a look at the chart and see if we can get any intelligence out of it, or out of me. Just before I get going on those measurements, I'm going to show you something else that I've spotted now in this radio, which is definitely worth spotting. So you can see here on the schematic it says wire gimmick, and it has this symbol indicating where the gimmick is. So we look up on the schematic and we hunt for that symbol. We will find it right here and here, kind of suggesting these two capacitors are actually a wire gimmick, and it goes to this switch. So I'll show you what I found in the radio. I'm sure it's this gimmick, but boy, you could look at this schematic all day and never imagine what it really looks like in the radio. So let's go take a look in the radio here. Okay. So I have seen a few of these in radios. Uses of gimmicks. Gimmicks is basically what they call a twisted wire around another wire. And that wire often not going anywhere. Can you see it in here? No, you can't. You can't pick it up that easily. It's right here. Can you see this green wire? It comes along, wraps around this heavy brown wire, pokes its head up the other side, and then bends and heads back down again and comes up this way. It's just connecting this terminal of one of the IF cans to a tube terminal. I believe these are the detector plates on the detector tube, I think. So the green wire and this wire represent the gimmick, but look at this brown wire. First, very heavy insulation on it, heavier than any other wire in the radio. And it just runs along the chassis. It goes all the way over to here. There, it picks up a terminal and then heads up for the switch up here. This is the AM CW switch up here on the panel. If you follow this wire beyond here, it's a gimmick. Tricky to see a gimmick. Oh, you can see it there. Comes along here, kind of disappears out of view. There it is there. Going kind of through the base of one of these IF cans. Isn't that a little bit odd? It's kind of twisted through there. I mean, wouldn't somebody normally just lay it down in here? Why is it in there? It's in there for a reason, I'm sure. And then the hardest thing of all to see, which I noticed earlier on, very hard to see, right up in here. Oh, give me something to point with, my orange pencil. Right here. The wire, I didn't notice this the first time I saw this metal band here, but this heavy wire is just cut clear, just out of view there. It just ends in space. This it's literally like a clamp, if you like a little piece of metal, runs back under the rivet of this tube socket here. No soldering, but riveted down in there. So this wire, which snakes through this whole thing, is a critical element for some reason in this radio. I'm not exactly sure what the gimmick is doing yet. So I think it's part of the, let's call it a pseudo BFO system in this radio. I'm not too sure about that yet. But so, you know, this is the kind of thing a very innocent person not used to this kind of work would look at that and go, that's a stupid thing. Why'd they twist that there and untwist it? Yeah, I've been that guy. I've been that guy. First time I saw a gimmick, I did not know what it was. And I thought, oh, somebody put this wire here. That's stupid. So one option you do have with not this one, not this scheme, I don't think, but other gimmicks can be replaced by small capacitors if you really want to do that. Okay, so that's the gimmick story. Now we'll get back to what I'm really doing, which is taking all those voltage measurements and completing my chart here. So just warming up this radio and hearing this. It reminded me of a video I watched yesterday actually on noise reduction in HF radio systems or antenna systems, and the video was really focused on a device made by MFJ, a antenna noise reduction device, and it's to beat back exactly this kind of stuff. And the way it works is you have your regular antenna that you're listening to on your radio, and then you have an auxiliary antenna. Maybe it would be right here in the location you're in, maybe stuck 10 feet away, maybe up on your roof. That antenna's purpose is to provide another signal to this MFJ device, and then there's a phasing control, and you shift the phase of the two, as I understand it anyway, of the two signals coming down from the two antennas, the one you're really listening to and this other auxiliary antenna. And if you phase these things just right, it's like noise canceling. It is noise canceling, isn't it? It's like noise canceling in headphones. You get it set just right, and one will buck the other, and you end up reducing the noise tremendously. The people who were, I watched a couple videos, the people who were using this device were getting excellent results. Not readily apparent when you listen to the radio that they're using. In all these videos, they did the same thing. They had a radio with a strong AVC. So sound-wise, the radio sounds the same. What you see is the S meter going up and down as the noise is knocked out. So you have an S meter high from high noise. And as you adjust this phasing control, you can see the S meter go down. The radio should get quieter, but it doesn't because the AVC cranks up the volume. So it's a little bit counterproductive in a sense. But boy, they were pretty excited with it. One guy said his whole ham radio station was ruined when his neighbor got a plasma TV. And it was unusable, and this device helped him get through that. So there are powerful approaches to knocking out this horrid noise that we all put up with these days when we're listening to these old radios, and new radios too. It's the same thing. They're all picking up the same noise. So thought that was interesting. Phasing out the noise. Okay, back to my voltage readings. Okay, let's take a look at these numbers and see what we can derive from it. So, pretty simple chart here. There's the tube numbers. Target means what I found written on the schematic. Actual is the measurements I took. There's only one AC measurement, that's this one here. All the rest are DC measurements. Some of these give a couple numbers, some of them actually give a range. So, a little different things going on here on this chart. So let's just take a look and see if we can eliminate a few tubes to be concerned about. This one I think we can eliminate. These numbers are close enough for now, but it is notable that this is a little low. This is the sort of the initial B plus, if you like. A little bit low. The radio was running at about 114 volts AC in the outlet. Okay, the output tube. So plate and screen. A little low again, but close, pretty close. And This is the bias. The bias is intended to be 5, but in fact it's 4 volts. Again, it's not much of a difference, not enough to really get me going here. So now we'll go down to the 12SQ7. This is the detector tube. So this one, you're supposed to find 0.7, minus 0.7, and I'm finding a third of that, 0.24. And this is slightly low, but it's a small voltage to begin with. And this guy's a little low too. This is probably the plate. This must be the plate on the tube. Okay, next one. Now things get a little complicated. These are this is the first tube and the second tube. Yeah, so this is actually the IF amplifier, this tube. So it's giving two target values, and that's based on what band you're switched to. In this radio, when you're on bands 2, 3, and 4, there is an operating condition set for the radio. When you switch to band 1, it's a different condition. And what is changing are these bias voltages here. On this tube, anyway, let's just concentrate on this one tube. So we're expecting it to be minus 0.4 on bands 2, 3, and 4, and higher, or lower, depends on how you want to look at it, minus 1 on band 1, the AM broadcast band. The actual readings are quite different. This is about a quarter of what it should be. Likewise here, not quite a quarter, but they aren't coming close to these numbers. Not sure what this is. This is maybe the cathode bias. I'm not sure what that reading is, but anyway, we're about half what it should be. But in terms of plate and screen, it's perfect. Whether this is a problem to be dealt with, I'm not sure. I haven't really thought that through yet. So this is an amplifier tube, an IF amplifier tube. Its business is pretty simple. Could be maybe these being off a bit doesn't really throw this tube into a tizzy, other than perhaps it's not amplifying as much as it could. I don't know. It's got the right plate and screen. Now, the key tube here in this radio, I think, is this one. This is sometimes they call this the first detector. I like to call it a mixer, but it could be called a frequency changer. I think if you're British, you'll like that. Frequency changer. There's a couple other names for it. So we'll take a look here. So this must be plate and screen at close. Well, they should be the same voltage according to the schematic, and they are. Well, they're getting their feed from the same wire, literally, in this radio. Now things get a little difficult here. So when switched onto bands 2, 3, and 4, the voltage of this terminal can be anywhere between minus 8 and minus 14. My guess is what we're seeing is AVC, and this is a hint of the range of the AVC voltage that one should find as you tune through strong and weak signals. Notice the lowest is minus 8. The radio, I believe, the AVC was not very active while I was doing this. I believe that to be the case. Let me look. You know what? I got an antenna hooked up to it, but I know the antenna is not switched down here. So just exactly where this should fall in this range under its current operating conditions on my bench, I don't know. Somewhere above minus 8, but in fact, it was below. Same thing on this side. So you switch to band 1, and you expect to get less bias here. It's about half. And you get about half, but again, it's low. It's below the lowest. Could this be responsible for some weird and bad behaviors in the radio? Well, if the bias is too low, in my mind, you could feed this with a signal that is greater than the bias, driving the signal grid positive. If the bias isn't lifted up high enough or low enough, depending upon how you want to look at it. This could be a problem. Okay, now the last thing on this tube, pin 8. Pin 8. What is pin 8 on this tube? Offhand, I couldn't tell you. just right offhand, pin 8. Minus 0.3, minus 1.8. Again, changing with the bands, and the actual voltage is virtually 0 and low. So when I look at this whole chart, the part that catches my eye is really this stuff, and this stuff. None of these seem to be coming out quite right. Like, could there be one factor throwing them all off? I guess that's possible. They're all a little low here. This is grid bias. They're all negative. This is grid bias. You know, what is this? What's going on here? Oh, two grids. Two grids, but the grids, 12SA7. So I don't know offhand where the grids are. What do you say we jump to the schematic? And we'll look at the 12SA7. And what are the grids? So the grid is 5, if you believe that's a 5, 5 and 8. And 6 is the cathode. Yeah. So we have the this is the grid for the oscillator, and this is the grid for the antenna signal. Grid for the antenna signal has a low bias. The grid for the local oscillator is much higher and varies from band to band. I sort of thought, you know, I'm not 100%. Hey, I'm not 100% on stuff. I kind of thought this grid is not normally biased. But so much for what I thought. How is it biased? Is it kind of a capacitor here, a resistor there? I think this thing develops its own bias on here. The bias on this is going to be, at the very least, the AVC voltage coming down through here. So 10 to 1. Most of the voltage here. AVC that way. So look at this. So we have the AVC line coming up here, and here the voltage is going to go on. Let's just look at band 1. Oh, yeah. Band. Let's look at band 1, 2, and 3. Bands 1, 2, and 3. Can you read that? 0.4. Minus 0.4. And then we follow this wire over here. What kind of voltage is happening up over here? 1, 2, 3, and 4. 0.3. 0.4. 0.3. And this resistor's there. That's probably why the 0.3 over here. It's a big resistor. So it's basically the same bias on the grid of this tube as you do on. Now what happens when you flip to band 4? You get minus 1.8 here, and you get minus 1. So it flips around. Now you've got more bias over here. So what exactly is being switched when these switches are thrown? Ooh, I have to go study all those switches. Not a lot of switches in here. One band switch. I don't like analyzing these band switches very much. Where is it? So here it is. Ay. So you're changing all these coils around. These coils have resistance. The resistance is varying. Maybe that's what's causing these variations in the voltage up here. Very big voltage on there. On the it must be derived from grid leak type potential. So what to do with all this stuff? So at this point, I think the best thing I can do. Let me flip back to the actual So I think the best thing I can do now is none of these voltages are like missing or something like that. So there's nothing grossly wrong with any of that, I would say. We know the radio already works to some degree, so I mean, how bad can it really be? So the next thing I think might be interesting in here is to think about those voltages and look at these old capacitors and try to figure out if any of these capacitors, if leaky, would pull down that particular voltage, the grid voltages in here. And then that'd be the good one to remove and see what happens after it's removed or replaced. Not holding down the grid voltages. We have to go back to the schematic again and ask that question. Okay, Mr. Schematic, which of these capacitors that I'm on my way to changing might affect these voltages here? Well, this guy. So what would happen if this guy were leaky? So he would pull a little extra current through here and drop this voltage. And then with this voltage down, not as much current would be pushed through here. Wait a minute, what kind of current can you push through there? It's a grid. Oh! So you might with this leaks, pulling a very small current, upset this whole AVC and grid voltage line. So you know, I don't know for sure, but I'd say that's one that could do it. And what about this one? So this guy's job is to let through the audio to the volume control but keep the DC away. Now if he's leaky, see a little bit of DC go through here, what does it find next? Goes onto a shielded cable, reaches the volume control at 2 megohms to the B minus. But the DC won't see this 2 megohms if this capacitor is good. So you look at the size of the resistances around here, that's half a megohm. You know, 2 megohms is not that far from half a megohm. Look at this one, 10 megohms here. So, you know, could this leak enough to drop the pressure here? You got a leak in the side of the can. This is fairly high impedance through here. Little leak might do it. So this guy, he could be involved, in my mind. What about this guy? Now this is a 220, it's probably a ceramic capacitor. It's probably okay, but if it were leaking, then again, a tiny current leaked to the B minus would drop the voltage here. I would think it would drop the voltage. So I got 3 of them now. Just basically every capacitor that's on the AVC line could be a bad actor. That's kind of what we're seeing here. Any more? What about this guy? Wow, that's a complicated one to answer. Again, it's a 220, it's probably ceramic, and it's probably just fine. But, you know, if that were shorted or leaking, you can't help the voltage on the grid, can it? You can't help it. Anything else? So what if this resistor is open? You know, it's not going to be. It's going to be fine. It's $500,000. If it's drifted to 600,000, it's not going to make any difference, I don't think. But over here, oh, whoa, 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 we run right headlong into this gimmick here. There's a switch here. On AM, a ground, a B minus connection is applied to the gimmick capacitors. You know, we looked at these. These are physical wires and things, and they can't be shorted or leaky, I don't think. So this would really be a question of, is this insufficient or like not enough capacitance here? What is this doing? Look, taking the plate, sticking it back on the grid. In AM, that is cut off. That won't happen, but in CW, it allows this feedback. So there's the feedback that's going to cause, it's right in the IF. Somehow trying to get this guy to generate a BFO effect. Could this arrangement, well, we can flip the switch here and we can see if the bias changes. No, I don't think this can affect the grid bias unless something horrendous has happened. No, I don't think so. What are we left with then? So what did I figure out here? Just go that guy, quite likely, and the guy on the volume control. That one. Let's try to find this one. First off, he's between two identical 2.2 megohm resistors, so that's red, green. Two red, greens with a capacitor in between. That should be easy to find. Let's find this guy. Okay, red, green with a capacitor in between. Hey, that sounds like a little, there's a red, yellow. So I'm just looking at the end of the capacitors. Oh, he's on a wire. And just looking to see if I can spot quickly. Hey, there's a red, green here, and a red, green here. Red, red, green, tied together. Where's the capacitor? Oh, so this capacitor ties to this pin which ties here. So this would be the capacitor here. The other side going to B minus. This and this are all B minus here. So that's the capacitor from this is the capacitor this is the ABC capacitor. That's what I want to say. Spit it out, Jim. ABC capacitor right there. Okay, let's get him out of there and then give him a test. I know it's going to ground. I don't need to leave a tail here. Okay, pull it out. 0.02. That's what was on the schematic. Now, let's try him out. How you feeling today, Mr. Capacitor? This guy's duty doesn't involve a high voltage. It just involves 10 to 15 volts. Okay, I'm going to hit him with 50 volts. You can watch the eye. Here we go. Never mind what you just saw there. Open right up. Phooey, 150. So this capacitor is in pretty good shape as capacitors go. Give him 250 just for fun. Still opening. So this guy ranks pretty high for a capacitor coming out of an old radio. Is this guy responsible for drawing down the ABC voltage? Wow. Well, I can't say for sure. This is a qualitative test. I mean, I know the quality of this compared to other tests I've done, but I don't know what that really means in terms of microamp leakage at 10 volts. I mean, yeah, not much voltage on it. Can't leak a lot of current without a lot of voltage. Well, we're going to put it in. I'm going to replace it and test that radio and see if those voltages change. So I'm going to go ahead with that on my own. Next time I come back on, we'll be looking at the chart with some new values that may have been influenced by the capacitor I'm about to replace. And in the meantime, I gotta go watch the news, like everybody. So I'm just finishing up on taking the measurements, and there's been a little bit of a change, but I've noticed something interesting. I think it's worth paying a little bit of attention to, so let me just see if I can safely get things ready. So looking through the wires there at the meter, and watch what happens when I wiggle the band switch. You have to move the band switch to take readings on 2, 3, 4 and on 1. And as I move, I'm just going to flex the band switch. I'm not going to actually turn it. Okay, we'll turn it now. As you can see, it's still wiggling around down there as I flex this. So the band switch has a role to play in this. Huh. So I'm going to clean up the band switch next and see, get that out of the picture for sure. Okay, so if you're an anti-WD-40 person, look away while I do this. Pretty busy little switch, wafer switch here. It has many, I think all the two wafers, and they're double-sided. There's 4 switching surfaces in here, I think. Lots of contacts in this one. Okay, and even, yep, down this side too. Usually when you do this, you can tell as you snap this back and forth that the oil and grease are being removed from the switch contacts, because it starts getting more and more grindy and feels more like, you know, bare metal sliding over a bare metal, which is kind of where you're trying to get to. Trying to wash off the oils, tobacco, smoke stains, all that kind of stuff. Well, it feels a lot different. Let's see if that stabilized the switch. Now is that switch, everything dinging and ringing in here? If that switch is responsible for the bad readings, only partially, if really at all. Let's give it a go here. While we're doing that, no, I'm going to do this first. Then we'll take a look at the results. I have them tabulated, so. Okay, watching the meter. Let's go on that other band because we get a higher number. There. Now I'm going to wiggle the band switch. Well, it's not moving as much. Still a little bit. Some of that could be as simple as I'm making radio noises. Radio noises. Maybe not. I was thinking I'm making radio noises and it's being turned into AVC voltage, and then it's affecting these things. Well, I'd say it's a lot better. Still wandering around there. They're wandering around because I'm making the radio wander around. Nope. Okay. So let's look at the results. Let's look at the results. What are the results? So the additional, I haven't written this one in here. The additional, we're looking at this a little early. The additional readings I just took are in red. This is the target, or what's on the schematic. This is my first reading. This is the renewed reading. Look, nothing changed here. This one changed. No, it didn't. It didn't change now that I look at it. It's the same. So changing that capacitor made no difference to these voltages. And what about this last one? 12SA7. So I can do those. You just look at the chart there. I'm going to grab... Oh, it's so easy to do. It's right here. So the actual reading is 0.52, and the other one is so close to 0 as to be almost 0. So I would say it's the same sort of thing. Minus 0.05, and the other one was minus 5. So slash. So there's quite a difference here between this minus 1.8 that the radio wants and the minus 0.5 that I measure. Yeah, these aren't really any different either. So changing that capacitor, for a while there I was hopeful. Didn't do much. Now the other capacitor was the capacitor blocking DC going to the volume control. Let's find that one. Let's take a look in here. I still got the radio switch on. Don't forget that. He says, talking to himself. So the volume controls here. Shielded wire. It's going down here with the two leads in it, going down under there. The shielding ends under this inductor. You can kind of see it down there. And then the two internal wires come up here, one here and one here. One of them you can see heads off to this capacitor and this tube, which is the detector tube with the triode in it, the audio triode. This is probably the audio signal coming from the volume control, heading to the triode in there. Then this would be the signal coming from the radio part of the radio and heading to the volume control here. This is the one that has a capacitor on it. I can see one connection right here, and it's going down to that capacitor. That guy is, other end of it is not connected to ground terminal. It's connected to some other terminal with lots of stuff on it. That's the guy we got to go after. That's the audio one. So that's the other one that could be pulling down these voltages undesirably, I guess is the word. So I'm going to go after that. Change that one out of there. I'm going to shut off the set. I'm going to cut that capacitor out of there and put them on the tester. And then I'm going to go and have lunch. So let's get them out of here. I'll leave a nice long wire tail here because when I come back, fat chance I'll remember what I was doing. I'll leave this tail sticking out here. Here I am. The other one is on this big terminal here. So I'm going to cut it right off the edge of the terminal. If I can get in there. Cutting air. Things that always look easy. There we are. Okay, let's get them out of there. This is a pretty dirty guy. Standard Condenser Company, Chicago, Illinois. 60609. Where's the numbers? .600 volts DC. There it is. 0.01. Wait a minute. 0.01. 0.01. I thought it was something else. A quick look at the schematic here for me alone, and that one is a 0.01. 0.01. 0.01. Good. Okay, I'm on target. Okay, I'll put the new capacitor in. No, I'm going to go eat my lunch first. Wait a minute. I can't go to lunch without testing this capacitor here. And this isn't it. Here it is. Lots of wax on the leads. Okay, 50 volts. Right open. Open part way at 150, 250. I don't think it'll open at 250, so it's a little leakier than the last one. But not as bad as many. Not nearly as bad as many that come out of old radios. So again, can this guy be responsible? Well, we will find out after lunch. Stay tuned. After I come back with full charge after after eating my ham sandwich. Okay, I've got that capacitor in. And not a ham sandwich. Fish sandwich today for lunch. Doke. Check the voltage here. That's going to settle in around 117 or so. Okay. A little volume. And I think I could just read, oh, here we are. Here it's coming up here automatically because I got it clipped on. It's going up and down. Seem to have lost a lot of volume. The radio is operating without an antenna. I will supply it an antenna. Oh, it does have an antenna on it. Oh boy. Well, wow, did I make a mistake? No, I did not make a mistake. No mistakes on the capacitor. Well, we won't worry about the low volume right now. That's a little bit unexpected. Let's check the voltage is here. So that's about 4.8. See that band switch is still doing funny stuff. So that's about 5 volts. So I'm just going to glance at my chart here very quickly and see that that was pin 5. That's what we're on there, pin 5. 6 and 3. What has happened here? I got a totally different reading. So, oh my gosh, this is the 1.5 volt scale. I must be on the, okay, hold on. Let me get my head together here. Okay, so we're looking at pin 8 here. 0.5 was the previous reading and 0.5 is the reading now. It's the same. So the capacitors had no effect, but a huge loss of volume. Man. Okay, so the problem I'm chasing right now, which is the bias voltage not being quite correct, I'm going to continue with just capacitor replacement in the radio. That's the phase I'm at right now. We'll kind of let that problem sit by the side a little bit. Later we can return to it. Maybe it will correct itself once I change out a few more capacitors. Quite a few things that could affect it, including even a weak IF tube or a weak detector tube. Maybe the diodes in the detector tube aren't all that good for some reason. They're just not getting enough voltage in the AVC system right from the start. So it's quite a few different things it could be. So I'm going to carry on. The goal is to get rid of the paper capacitors. So is there another one that might be significant in this? This one's over in the audio output tube, so that can't be part of this. So we got this guy here and a guy there, and I think that's it. I'm just going to knock those two out of there, and we'll check again and see if there's any improvements. Maybe the volume will come back. Kind of doubt that. Oh, it took me about 2 seconds of looking at this radio to realize why the volume's gone. I put that capacitor in the wrong spot. Jeepers, creepers. Okay, I'll fix that. Okay, let's just test this radio again and see. Off, on. Seems like if there's any way to get a capacitor installed wrong, I like to try it out first. We got some volume again. Still seems a little low. This is way high. Oh. Well, goodness knows what's going on here. Let's just keep going. At least I've got the volume back, most of it anyhow. And okay, the last two capacitors. Oh, there's three of them in here. There's one, two, and that one. Well, we'll do them. I'll do them. Let's take a look at this schematic for a second here. The capacitor I've just cut out is this one, 0.003 down here, and it's grounding, it's providing a signal ground at the bottom of this tank circuit here coming off the plate. So so if this isn't pulling this line down to signal ground, if it's not grounding the signal here, signal will be passing through this guy, and you won't get as much out of here as you could, which means you won't get as much detected here as you could, which means you won't get as much voltage way back here where I'm making all those measurements as you could. So maybe this guy's the bad actor, so I'm going to change him and turn the set back on. I think the last one that's in there is this one, I think. Oh, that's an interesting one too. Let's get this guy changed out and see if the radio's better. Okay, time for another test. So we could get more volume from this. More volume, maybe more output from the IF, maybe more voltage on the meter there. It's the same. This is coming up 0.5, all the same. This seems a touch higher on the 1, 2, 3 bands. Oh. Okay. At least the radio's still working. I mean, part of turning it back on is making sure it's still working, because that's pretty necessary in my case. The last one is this one here. Pop this one out, and we're going to test the two I just took out. I'm memorizing its location so I don't make a mistake. How humorous can that be? Come on over here. Oop, 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 oop. This is the one I just took out. 50 volts. So these capacitors are proving them, that's not so good, to be not the worst. That's about the best I can say about them. They're not the worst. 50. Wow, look at that one. This is the one I was hoping was causing a problem, but look at it. It is working just perfectly. Perfectly fine. In fact, we can read the capacitance on this one accurately. I think it's a point, what is it? 0.003. So if it's a 0.003, it would be on here. This one here. Now we'll swing this till we see the eye pop open. It's way down towards the end here. That's the spot though. 0.005. And 0.003 is just a short ways away. So it's measuring a little high, it's a little leaky. That all makes sense. Is it worth changing these? Is this making enough of a difference in the radio that it's worth the buck per capacitor? Sure. What else am I going to say? Last one to go. Way down here. Oh, just revealed something there. There's a resistor here. Doesn't look too good. Now, I think it looks like that because it was sitting on this. This was sitting on it. And I think this is just wax that's gotten onto the resistor, making it look different, but I don't think there's any problem with it. This guy here is a .600. Might be under here. Point. Looks like 0. Oh, I just rubbed it right off. So this one's come from the output tube, and let's take a pin number. It's on pin number 8 of the output tube. Okay, I'm going to take a quick look at the schematic here, and I'm going to say pin number 8 of the output tube is the cathode. There's no capacitor there. Okay, let's try that again. Okay, I don't know. It also goes over to pin 1, 2, 3, pin 3. So let me look on the schematic here, up on pin 3, and oh, there it is. I missed it. Yeah, it's definitely there. It's a 0.02. It's a 0.02 right there. Okay, I'll install the new one. And why don't we test that one right now? Put my tester back on, and we're done with these capacitors. Volts. Well, you know, I have seen worse. I think I've definitely seen worse. I've definitely seen better in old radios like this. So we'll put in the O2. I'll get that done. Okay, last capacitor in. Now let's see what happens this time. The primary reason I'm testing this is just to make sure it still works. Maybe the radio's quiet because I have this meter connected onto it. volume still seems low, like much lower than it was. So I'm going to disconnect the meter. The meter is reading 0.5, exactly the same voltage again. Okay, we'll pull it out of there. Nope, it's not dragging down the voltage. Kind of a high impedance hum sort of sound there. I don't like it. Okay, let's go band 1. I have to go and throw the antenna on. Maybe 1 second. Okay, radio, what do you pick up? Wow. Oh, hey! Okay, that's good. It's working. That's good. Okay, so I'm going to stop at this point for today. That's the end of the paper capacitors. And we still have some weird voltages on grids. Not sure what that's about yet, but there could be lots of other things that could be causing that. Some tube testing may be next. Maybe I'll start off on the next video with tube testing, and just to make sure we don't have a weak tube in here. And there we are. Fantastic. Hey, thanks a lot for watching, and stay safe.